All right, week 7, here we go. So we are wrapping up the idea of looking at higher degree polynomials. And basically today we're talking about, or this week, it's just one day, it's both. We're talking about polynomial division, which is what happens when you divide one polynomial by another. I'm not going to write another thing. Here's an example. The thing on top is a polynomial. The thing on bottom is a polynomial. We're dividing, that's polynomial division. There are sort of two varieties here. Long division, which works a lot like, I can't write the word division. Long division, which works a lot like, okay, all right, everybody just take a breath. Long division, which works a lot like long division for numbers. So the division algorithm you would use to sort of do a division by hand. And synthetic division, which is kind of a little bit of a shortcut kind of way of keeping the books a little bit differently. I'm going to do both in a second. I'll do an example with this one in just a second here. But the reason that we're doing this is mostly because of this thing called the factor theorem, which we've been using already. But what the factor theorem says that a polynomial f of x has a 0 at x equals a if and only if x minus a is a factor of f of x. So we've been using this for a while in the sense of, using factoring to break a polynomial up, and then using the zero product property to split the factors up and use that as a way to solve. That's taking a factor and using it to find a 0, which is basically going that direction in this theorem. We've also used the other direction of this in interpreting graphs and saying that if we know a 0, then we know about a factor, right? So if I start with a graph and find some zeros, then I can identify factors. We've done that as well. So factor theorem says that these things are always true. Like the only way to get a 0 is if you get a factor, and the only way to get a factor is if you have a 0. So I can't have, say my function was, I don't know, x minus 1 times x minus 4. The only zeros are 1 and 4 because the only factors are x minus 1 and x minus 4. So that's what this theorem says, that all of the factors correspond to zeros and all of the zeros correspond to factors. We'll see how we're going to use that in a bit here. This is a special case of a thing called the remainder theorem that says basically the value of f of k, so just some number in evaluating the function, is this, I don't know why I don't say is equal to. Is equal to the remainder from dividing f of x by x minus k. So the factor theorem is the special case of that when that remainder happens to be 0. Because if the remainder is 0, that means that the value of the function is 0, which is places where you cross the x-axis. Okay, so this is the more general thing. For the most part, we care a lot more about this special case, though. So that's the thing we're going to emphasize. Okay, we'll talk more about that in class and like what that means. But there are the statements of those two results. Now let's look at what the how we actually do the division. So again, what I want to do is divide x squared plus 5x plus 6 by x plus 2. So here's what that looks like using long division. Just like we would do with doing long division of, two numbers. I set it up something like this. Now, long division for numbers, like say I want to divide 40 by 3. The way that works is you start by looking at how many times this goes into this, right? 3 goes into 4 one time, and then I multiply 1 times 3, which is 3, and then we subtract, and 4 times 3 is 1. And 3 doesn't go into 1, so I carry the next place down. But 3 does go into 10 3 times. And then I multiply again. 3 times 3 is 9. I subtract. There's a 1 left over. If we were going to keep going, we'd add a decimal point and keep going as long as we wanted to. Otherwise, we say that this is the remainder. So 40 over 3 is 13 with remainder 1. Right, that's how you interpret that or read that. The quotient, the answer, is 13, and the remainder is 1/3. Or the remainder is 1, which you can write as a fraction as 1/3 because you were dividing by 3. So long division, by hand like this is really just a way of giving us sort of a framework for chunking the dividend, the thing we want to divide, into smaller pieces. We do the exact same thing with polynomials. It's going to feel a little different, of course, but we look at the leading term, and assuming I don't know right off the bat how many times this whole thing goes into this, I chunk it up into smaller pieces. So I only look at the highlighted things, and I say, okay, well, what happens when I divide x squared by x? And what happens is that you get x. Then we multiply like this and carry that down to figure out how much of this we've sort of accounted for already. X times x plus 2 is x squared plus 2x. And then we take that away to figure out how much is left over. X squared minus x squared is 0. That's good, because if it wasn't, then that means I could have taken a bigger chunk before. 5x minus 2x is 3x. And then I'm also going to carry the next place, the next term down, or just think about it as subtracting 0 from 6. So I get 3x plus 6 left that I still need to sort of account for or figure out if this thing is going to divide into this thing. So that's one step of the algorithm, and then we just do it again. Let me erase some of my stuff there. Okay, so now I'm going to look at how x divides into 3x. So if I take 3x and divide by x, we get 3. That goes in 3 times. And then I'm going to do the same thing. Take this, the new part of the quotient, and multiply. 3 times x plus 2 is 3x plus 6, and then subtract. 3x minus 3x is 0, but 6 minus 6 is also 0, so this leaves remainder 0. Remainder 0 just means that it goes in evenly, right? It goes in a whole number of times. So what this tells me is that this division is x plus 3, or in other words, x squared plus 5x plus 6 is equal to x plus 2 times x plus 3. Now, this one we could have factored other ways, like normal trinomial, factoring works here. You can find numbers that multiply to 6 and add to 5, and they're these. So we could have factored this other ways. What this really does for us is kind of expand what we can do with factoring and help us to factor things that would have been difficult or unreasonable to do otherwise. It helps us see things that I might not have noticed if I just looked at it. But you can see then how this is going to tie into this factor theorem idea that we talked about. Okay, and now I'm going to do the same problem with synthetic division. Okay. Long division is kind of showing the full, the full details of how everything works. Synthetic division basically says, hey, what if and by the way, synthetic division only works for a linear divisor, so the thing in the denominator has to be degree 1, or synthetic division won't work. But synthetic division basically says, hey, what if I took just the most important parts of all the stuff that just happened and just kind of boiled it down to what I absolutely need. Synthetic division is a little more of a trick the first couple times you see it because it is a shortcut thing, right? It's sort of an artificial, what if I took this and threw away some of the stuff that's not necessary. The way we do that is I take these things and I just use the coefficients, and then I keep track of what's what by the order I write them in. So the coefficients of the stuff on the top are 1 and 5 and 6. So I just take those, 1, 5, and 6. But again, now I'm preserving what they are by where they are. If I rewrote this like that, it wouldn't change anything about what it is fundamentally. But I would not be able to do synthetic division the same way without first, switching or keeping track of the fact that 5 is the linear coefficient and 6 is the constant term. So that's kind of the difference. Okay, so then I give myself a little sort of a framey kind of thing. Put a little box here. That's where the divisor goes. We're dividing by x plus 2, but for synthetic division, that means I take essentially the 0 that would correspond to that, right? So I take -2 and stick it right there. That's sort of the setup. Now, the way the actual algorithm works is that you carry this down to begin with. So 1. And then we multiply here. -2 times 1 is -2. I store that in sort of the next spot. And then add right here. So if you think about what was going on here, what we're doing is keeping track of now the linear term. So we figured out how many times it went into the quadratic term, what the coefficient should be. Now we're doing that for the linear term. So we add these. 5 plus -2 is 3. And then we do the same thing again. So I'm going to erase some of the stuff there, just so there's a little bit less kind of in the way. Change colors too, maybe. So now I look at these and multiply. -2 times 3 is -6. And then again, we add down the column. -6 plus 6 is 0. And that last position gets kind of boxed off as well. So what this shows me this is the thing we divided by. That's the quotient or the answer. and specifically it's the coefficients for the quotient, so we'll look at that in a second. And then this last part is the remainder. Now keep in mind, we already know what the answer is because it's the same problem. So what we got is that when I divide x squared plus 5x plus 6 by x plus 2, I get x plus 3. Now, in the same way that this preserves what things are by the order they're in, that this is x squared and this is x and this is the constant term, the degree is 1 smaller because we're dividing out by a linear thing, right? You take x squared and divide it by x, you're going to get first order thing. So these are the coefficients, x plus 3. So again, we learned the same thing, that this is x plus 3. Okay, so that's polynomial division. Again, I know that the first couple of times you see this, and until you've kind of worked through a couple on your own, it's going to feel sort of mysterious. The stuff that we're really going to emphasize and do a lot with is going to be, again, talking about the factor theorem and how that applies, which means that we're dealing with linear stuff, which means that synthetic division should be plenty to sort of get you through everything that we need. So maybe do a couple where you kind of try the long division idea, but if you like synthetic division better, you can pretty much latch onto that and just stick with that. Again, it's a technique, it's an algorithm, so it's going to be a thing that until you've done it a few times and it starts to click into place, it's going to feel a little bit artificial and strange. So yeah, I hope that gives you an idea of what to expect and a place for us to get started. We'll do some more examples and stuff in class, of course, but now you've at least seen it once. So thank you, and I will see you in class.